you the host access tab like I did yesterday, and the recording will begin automatically, and then I will dial out of the session. So in case you need me for anything in between, just drop me a quick email and I can jump in and have a look.
Absolutely. Thanks.
Right. All right. I think we are about time, so I'll stop the webinar now so that the attendees can dial in and they will be able to see us and hear us while we are still on camera.
Yeah.
Right.
Thank you, Manny, to give your plenary speech. Always.
Recording in progress.
Manny, it's your turn. We will wait a few minutes.
Yeah, we'll give it a couple
People
of
are
minutes.
joining the session.
Start.
Yep.
Sean, perhaps we wait for 30 seconds to start.
Yep. That's
People are
idea.
participating online.
Sure.
It's morning, yeah. People are just
Yeah, they're popping up.
finishing their coffee.
Shall we start, Manny? Are you ready?
Yeah, I mean, you're the boss.
So good morning, everyone. This is our third plenary speaker, Professor Manny Illuminati. Professor Illuminati has been known to many people as Manny. Manny has a WeChat name called Mo Wang. If I translate literally, it means the king of membrane. You may notice this by reading Professor Manny and his students' papers with a lot of inspiring theory, deep understanding. In recognition of his research, he received many renowned awards. Among these are any awards for protection of the environment in 2015, election to the National Academy of Engineering in 2006, and the Chinese Academy of Engineering in 2017, and the Clark Prize for Excellence in Water Research in 2005. Professor Illuminati are highly involved and contributed significantly to educate young generation researchers. Manny has advised 43 PhD students and 37 postdocs, many of whom are holding leading positions in academia and industry. I would talk a lot about Manny's achievement, but given his influence wide recognition, without further ado, would you please join me to welcome Professor Illuminati to present his talk in selective ion transport in membranes with sub-nanometer pores. Manny, it's yours.
Okay, thank you, Tao, for this kind introduction. I will share the screen. Let's see. So I guess you can see me now. Okay, great. Let's see, I will just find my laser here. Okay, I cannot see it here. So you can see me. Okay, great. So thank you so much, Tao, for the kind introduction. And I'd like to present today on selective transport in membranes, and I will start with just a small background. Again, we all know that there is global water scarcity, and it's really become worse because of climate change. And if you look at these maps here, if you look at the map, this is the map for 2020, the water stress around the globe. And if you see darker colors, it means it's really, there is some water stress there. And if you look at the laser here, now we go to 2030, much more, and 2040. So again, we do not have enough water, and this is where membranes come in. Again, we can use membrane for desalination of seawater and reuse of wastewater. And this will be the main part of my talk. So I would like to show you the evolution of what I call next generation desalination membranes, which will also be the outline of my talk. I will talk very briefly on ultra-high flux membrane just to connect with the rest of the talk. I will talk also about water salt selectivity, and this will be sort of like relatively short, and the main part of my talk will be on ion-ion selectivity, which what we think will be the future, and we see already a lot of research in this area of ion-ion selectivity. So let's start with the first topic, ultra-high flux membrane. And again, I'm here just recapping what probably already known, but I would like just to have a continuity of the story. Again, first, membranes play a key role in seawater desalination. Again, if you look at the seawater desalination plant, this is the reverse osmosis stage, and the membranes here are the thin film composite polyamide membranes. They are the state of the art. They were developed in 1980 or 81, and since then they are still in use. So this is the membrane that we really want to have a better membrane than it, or to beat this membrane. So this is a lot of research that we're doing. And the first phase of research, it was until about 5-8 years ago, it ended, is ultra-high permeability membrane. And again, the idea was if you can get these novel materials that can pass water at a very high flow rate, like carbon nanotubes or atom thick graphene, you can really have a quantum leap in desalination. And the reason they thought if you will have high permeability of water, you will need less pressure, and then you will need less energy. And again, as you see, there were a lot of papers published in this area. And mostly, again, a lot of them were fundamental papers, but again, some of them claimed that this will be the future of desalination. And as you know, it's a very exciting area of research. You can learn a lot about the properties of liquid in under confinement, dielectric effect, transport of water, slip boundary conditions. But when we come to energy of desalination, it has a very, as you see here, negligible impact. If you plot the energy consumption versus water permeability, again, these are three types of seawaters with different salinity. The water permeability of current membranes is here. So it means anything beyond it, going all the way high to 100, which is the ultra-high flux membrane, will not have any impact on the energy of desalination. So this was the first phase of research. And again, I said I will cover it very briefly. Now let's go to the second phase of research, is water salt selectivity, which is an ongoing, started roughly about 10 years ago, and still we have a lot of research. And the idea here is how to get very high water salt selectivity or high salt rejection, which will have a lot of benefits. And again, you can see this idea in this permeability selectivity trade-off diagram. This is the selectivity or the water salt selectivity. We need to get very high water salt selectivity or high salt rejection. This is water permeability. What I showed you from the first part, that going to higher water permeability will not do any good for desalination. So we need to go probably to high water selectivity going in this direction, or maybe slightly in this direction. And again, there were plenty of research in this area. A lot of these novel materials, carbon nanotubes and synthetic channels and graphene. And I would like just to say a few words before getting to the main part of my talk, which is ion-ion selectivity. And again, there are plenty of papers on graphene, plenty of papers on other two-dimensional materials, and and as you see here, molybdenum disulfate. And the problem is these membranes, that although it's exciting, there are a lot of fundamental research, it's very difficult to get a membrane with very high salt rejection. Again, we cover it in some of our papers. And the reason is that you have framework defects. If you have these layers and you build them 1/1, as we do with two-dimensional lamellar membranes, these framework defects are interconnected, and you need to really get very, very, very thick membrane to avoid these framework defects. But if you get very, very thick membrane, also the permeability drop below acceptable level. So, and again, we see these framework defects again in literature. If you go to this kind of two-dimensional membranes, this is from the literature, you see clearly that there are some defects and the layers are not horizontal. And some other papers, again, this is our recent paper that showed it's not horizontal, so it means you will get all these defects. So this brings me now to the main part of my talk, and again, and this will be ion-ion selectivity. And again, this is sort of the frontier, the future, and why ion-ion selectivity is important. So again, at the water energy nexus, we have membranes, and these membranes need to be very selective, like in electrodialysis. We need to have cation exchange membrane or anion exchange membranes. We need to design them to be highly selective, so they will pass only here just cations and no anions. In nanofiltration membrane, if you can develop a membrane that can be selective for monovalent and divalent, like lithium and magnesium, by a very high ratio, then you can think about recovery of lithium, for example. And the same thing, energy conversion technologies like electrolyzers or fuel cells have proton exchange membranes that should be selective. We can also think about critical removal of some selective removal of some ions from industries. This is part of the circular economy, and you can think about recovering of lithium from brines that also have sodium and potassium, for example. Electronic waste, you can digest this waste, and if you can recover these metals, it will be great. You can think about lithium-ion batteries, again, recovery of lithium from electronic waste, and some from wastewater, like nutrients from wastewater. So the problem with the current polymeric membranes that we use nowadays, that they do not have very high selectivity because the mechanisms there are relatively simple. They can be either by size, as you see here, or charged by Donan exclusion. And although this mechanism can give you some selectivity, it's not high enough, or it's not sophisticated enough. We really need some better approaches. And we can, of course, rely and learn from nature. The biological channels, specifically the potassium channel that was developed in evolution of close to 1 billion years, is really one of the most amazing selective filters that you can ever find. And let's look at the potassium channel. Again, the thickness of the potassium channel, or think about the membrane, is only 12 angstrom, 1.2 nanometer. Now, it's very narrow opening, narrow channel, and when you have a potassium that comes here, the potassium is larger than the opening, so you need to dehydrate. The potassium sheds some water molecules, and then can enter the membrane. But once you shed water molecules, it's energetically, it's not favorable. The potassium doesn't like it, but the potassium channel is carbonyl group with oxygen group here. And when the potassium comes here, the carbonyl binds to the potassium, so it feels like it has the water molecules around it, and then it's moving by hopping from side to side. Based on this principle, I summarize what I envision the principles to guide the design of highly selective membranes. We need to have small pore size, greater than the hydrated radius of the ion, but smaller than the dehydrated ion, so that the dehydrated ion can enter. We need to have the right binding site in the right chemistry, probably oxygen containing group if it's potassium, for example, and so you can have this binding to compensate for the energetic penalty of dehydration. It need to be a thin layer, because if it's very thick, it can be selective, but the transport rate would be very low, which is not good. And you can have another effect. The design of this spacing should be in such a way that it's really, this potassium can push the other potassium here and move along the channel. So with this introduction, I would like to cover two projects. One of them just simple, how we can understand the transport of ions through reverse osmosis membrane. And the other one is the precise separation of divalent cations by host gas chemistry. So let's start with the first one. It's very common to present the transport of ions through membrane by an energy barrier or activation energy. And this activation energy, again, if it's high, like here you see the red ions cannot go through, so you can prevent the transport of ions. And if the energy barrier is low, as you see in the blue line and the blue ions, they can go through. And the reason you can get this energy barrier are listed here, but again, it's related to the pore mouth and also through a friction or interaction when you move along the pores. So what I would like now is really to first go over the limitations of previous studies that try to understand the transport of salt through reverse osmosis membrane. Although we have reverse osmosis for many, many years, 60 years, we still do not fully understand how water and salt going through. And let's see, when salt going through, you can think about it, you usually do experiments by diffusion cell. You have salt on the side, you measure what's coming out. And if you do the right experiment at different temperatures, you can present the flux as a function of the activation energy and calculate the activation energy for the transport of salt. So this will give you the activation energy for the transport of the salt, cations and anions. So we do not know how the cations and anions move individually. Another limitation of current studies that they assume that most of the energy barrier is due to partitioning. They assume that once the ion enters the membrane, it needs to dehydrate, and most of the energy barrier are into this partitioning step, and they did not quantify what's the role of intra-pore diffusion. Once you enter, what's happening when the salt is diffusing. Now, what are the potential mechanisms for transport here? You can think about it, and there are some that claim that the ions are moved as an ion pair. The cations and the anions, like sodium and chloride, are close to each other, like holding their hands and crossing the membrane, and this is what we call ion pairing. The other school of thought, and again, it's more accepted, is they move individually. If the membrane is negatively charged, the cations will move first. You will establish a membrane potential instantaneously, and then this membrane potential will accelerate the transport of anions, slow down the cations, so eventually you will get anions and cations at the permeate, and you will have electron neutrality. So this is what really we wanted to study, and I will not go, I know we don't have enough time here, but you can analyze through what we call a thermodynamic cycle, what can happen when ions move from a high dielectric constant of water here to a low dielectric constant inside the membrane. And when you analyze it, we can say that if we can measure the energy barrier for the salt, and if we can find a way to measure the energy barrier for the individual anions and cations, so if you have sodium chloride, I can measure the energy barrier for sodium chloride, but if I can measure also the energy barrier for chloride and sodium, if the sum of the energy barriers for sodium and chloride is equal to the energy barrier for the salt, then we know that they move individually. So now we need to find a way to measure the energy barrier for these individual ions, like anions and cations, and this is what I'm going to describe. So first, when we measure just the energy barrier for the entire salt, we just do a diffusion cell experiment. Again, you can put salt here on one side of the membrane. You can put another membrane here. and then the salt will diffuse, and you can measure these by conductivity. And if you do these measurements as a function of temperature at each different temperature, then you plot the salt flux versus 1 over the temperature, and the slope will give you the energy barrier for salt transport. So this example for sodium chloride, the energy barrier for the transport of the salt, which is sodium chloride, is 18.2 kilocal per mole. We can also study the transport, individual transport of the anions by this electrochemical method. You can have a membrane here. On both sides of the membrane, we can have the same salt concentration, the same, think 0.1 molar, for example. And then we have silver chloride electrode. And if we apply a voltage, the cations will move to the negative electrode. The anions will move to the positive electrode. And we do a separate experiment to quantify the membrane potential, from which we can calculate the transport number. And once we have the transport number, we can quantify and we can write the equation for the anions and the cations. And if you plot, again, this is more like the Nernst-Planck equation. If you plot this conductivity times the transport number as a function of 1 over the temperature, now you can get a slope for the sodium, which is the cations, and a slope for the anions, and these are the energy barrier for individual ion transport for sodium and chloride. Now we go for a range of salts, and you already see the result if you're quick to figure out what's going on here. This is the activation energy for sodium fluoride, as you see here, sodium chloride, sodium bromide, and sodium iodide. The blue bars are the energy barrier for the entire salt. So it means for the sodium and the this is sodium fluoride, sodium chloride, sodium bromide, and this is determined by just by the concentration gradient diffusion type experiments. Based on the method that I just showed you, the electrochemical method, I can quantify the energy barrier for the, here you see the cations, sodium, all of them will have the same cations, and this is the anions, in this case fluoride. And you see that exactly the salt, the energy barrier for the entire salt transport is equal to the sum of the energy barrier for the cations and the anions for all the salts. And also we got the right trend, the fluoride, that fluoride is the highest hydration energy. I will talk about it later. It's more difficult for it to dehydrate. So this will have the highest energy barrier. And iodine is the lowest hydration energy. So it will be easier for it to dehydrate, and we get the lowest energy barrier. So based on these experiments, the conclusion is the transport of anions and cations is independent in salt passage. They move independently. Of course, they somehow close to each other because they need eventually to appear in the permeate to have electron neutrality, but they do not transport as a pair. And this is a very important contribution for this literature. Now, let's see now, get in more detail and talk about the activation energy of these different anions. We qualify for the anions fluoride, chloride, bromide, and iodine. And I'm also here showing you the hydration energy, which tell you how tight the water molecules bound to these ions. Fluoride is the smallest ionic radius, so it has the highest hydration energy, as you see here. And naturally, it will have the highest energy barrier because it's more difficult for it to dehydrate. Chloride will follow, bromide and iodide. So you see that the trend of the energy barrier, the blue, follow the trend of the hydration energy, which is good. But now we compare sodium and fluoride, and we see things that is quite interesting. Fluoride has higher hydration energy. So it means it's more difficult for it to dehydrate, or we expect it to have higher energy barrier, but we see that sodium, which has lower lower hydration energy has higher energy barrier. So why we have this difference in the energy barrier that you see here? The sodium has higher energy barrier. So this is a question that doesn't follow this hydration energy that I showed you here. And indeed, we can explain it. If you go to this diagram, if you talk about the sodium, the cations, remember, reverse osmosis polyamide membrane are negatively charged. They have carboxyl group, as you see here. And when the cations flowing through here, the cations will interact with the carboxyl group, and which is slowing it down, and then interact here and interact. So this will increase its energy barrier because it's bind, and then you need to come off. And this is why we saw here the energy barrier for sodium was high, even though it has lower saturation energy. As opposed to, in this example, fluoride. Fluoride is negatively charged. The carboxyl group here of the membrane are negatively charged, deprotonated. So it doesn't have any interaction, so it moves relatively easy with less energy barrier. Again, it's all relative. And this explains, again, electrostatic attraction of the cations with carboxyl groups hinders intra-pore diffusion. So again, this is related to intra-pore diffusion. And as opposed, the intra-pore diffusion of anions, fluoride, is fast without any notable interaction. Okay, and we prove it by doing experiments at different solution pH. This example, again, we have the energy barrier for sodium and fluoride, but at 3 pHs, 9.5, 5.5, which is most of the experiment I showed you earlier, and 4.5. And you know the carboxyl group in the membrane at 9.5, there will be most of all of them will be deprotonated. So indeed, the sodium interact with many more carboxyl group, as you see here. And this is why we get high energy barrier. When you go to pH 4.5, less carboxyl group are deprotonated, so the interaction is weaker. And this explains again what we see here. Now for the fluoride is the opposite. The fluoride, the energy barrier will be determined by the partitioning step. This is by the diffusion through the membrane. And because in this case, for example, the membrane is highly negatively charged and the fluoride is negatively charged, the interaction is not favorable, so it's more difficult for the fluoride to partition into the membrane, which translates to higher energy barrier compared to the lower case. So this explains now that you have a intra-pore diffusion that can be important. And now I would like to see what's the relative role of intra-pore diffusion and partitioning, because both of them happening, the ion need to partition and then diffuse through the membrane. So we go through these analyses that permeability is roughly equal to the partitioning times the diffusivity. We can write, again, this is for the entire salt. We can write each one of them as an activation energy related transport. So again, this is the activation energy for the salt, activation energy for the partitioning, activation energy for diffusion. And if you look at this mathematics here, it tells you that the activation energy here is simply the sum of the activation energy of partitioning and diffusion. So now I would like to show you how we determine, distinguish between them. The energy barrier for the salt, I already talked about it. If you do diffusion type experiment with, as you see here, we can get this energy barrier. Now we also found a way to determine the energy barrier for partitioning. We take a QCM, quartz crystal microbalance with dissipation. We put a polyamide membrane. We dissolve the polysulfur by having a DMF, and eventually we're left only with the polyamide membrane. We expose this to salt, different salts, sodium chloride, sodium fluoride, sodium iodide, and measure the uptake of the ions, and this will be reflected by the change of the mass of on the membrane. This instrument is very sensitive. We do the experiment at different temperature, and we assume Arrhenius type equation, and we can find the energy barrier here. And when we look at this data, we see quite interesting. the activation energy for partitioning is the lowest one, you see here. And the right trend, fluoride, the highest energy barrier, more difficult to dehydrate, and you go in this direction, and intra-pore diffusion dominate. As you see here, we can calculate the intra-pore diffusion by taking the energy barrier for the salt minus the partitioning. So we found that intra-pore diffusion dominated transport. So this is quite important finding. And again, although intuitively you think this is the case, but previous study assumed that partitioning is the most important step. So I would like now to go over the second part of my talk. And again, I want to also have some time for questions. I was told by Tao to finish 35 to 40 minutes. And I would like to talk about highly precise ion separations through polymeric membrane via host gas chemistry. And again, this is the potassium channel. The interaction here are very important. And the transport, as I showed you earlier, is by binding and hopping from site to site. So we wanted to mimic and learn it, but we took, of course, a much simpler system. And I would like to show you a layer by layer approach to study it. And in this layer by layer approach, we take a polyelectrolyte, which is negatively charged PDCMAA, that we synthesize. And this PDCMAA is amino diacetate group, as you see here. And this amino diacetate have a very strong binding to divalent cations. And we took PAH that we all do for layer by layer, and we did layer by layer of the PAH, then the polyanion, and then PAH, etc. And as I told you, we synthesize this polymer because it's not available commercially. We take PAH, we react it with chloroacetic acid, and the right cooking recipe, we can get this polymer with this amino diacetate. Now we wanted to study the separation of a set of divalent cations, magnesium, zinc, copper, nickel, and cobalt. And this is the ionic radius, relatively close to each other. And this is the hydrated radius. And this is the ionic radius, relatively close to each other and the same charge. And let's see if we can really separate them in an efficient way, using the principles of the potassium channel or binding and hopping from site to site. We quantify the binding energy of these metals, as you see here, by DFT calculations and also verified by literature. This is the copper, nickel, zinc, cobalt, and magnesium. And the copper binds the most strongly to this amino diacetate, as you see it here. You see a very high binding energy, and the magnesium is the lowest one. And all the others are listed here. So now with this different binding energy, and we have these membranes with amino diacetate they can bind these metals, we wanted now to test their transport. And we say, okay, let's start with these two extremes, magnesium and copper. Quite exciting, different energy, big difference in the energy of binding. So these are the ions, almost the same size, but much different binding energy. We study it in a diffusion cell, as you see here. And here I'm showing you just experiment for single salt. When we measure just magnesium chloride, again, we measure the concentration versus time of the magnesium, we get this slope. So the slope will be the flux. And when we measure for copper chloride, another experiment, we measure this slope. So we can see that the flux of magnesium is higher than copper, maybe because magnesium has lower binding to the amino diacetate. But again, this is not important because we need to study what's happening in a mixed salt, because selectivity when you have both of them together. And we speculated the following. We speculated if we take the copper, the strongly binding, and the magnesium, we speculated two mechanisms. One of them, we can think about site inactivation, in which the copper bind very strongly to this amino diacetate, stay there, and if it stays there, then these ions, the rest of the ions will go through and you will get very low selectivity. And the other hypothesis was that you have again, binding, but not strong enough, so you can get binding and hopping from side to side because of the chemical potential difference here. Ions will move in this direction. And the magnesium, because it cannot bind here and cannot participate in this hopping mechanism, we assume that it will just go through and we can achieve very high selectivity. So this was quite interesting, approach, and we will see what's happening. Let's go back. Now let's go to copper and magnesium. Remember, single salt, it doesn't have any meaning, but just to show you what's happening when you have a single salt experiment. Just magnesium chloride, one experiment. Just copper chloride, another experiment. So if you can define a selectivity, it will be 0.39. But again, selectivity doesn't make sense here because selectivity is always when you have a mixture. Now let's see if you have a mixture. And here we got exactly what we expected. If you mix the magnesium chloride and copper chloride at the same concentration, and the experiments were done at a low pH, 3.6, so the copper will be copper 2+, we see that the copper, even though it's binding very, very strongly, we got the highest flux. And magnesium, we almost got nothing going through. And we got selectivity of 60, close to 63, which is amazing. So it means that our hypothesis here of this hopping from side to side can be valid. So we were very happy. So remember this one, single and multi. And then we went to do single salt experiment with the other ions. And remember, this is the binding energy. With copper and magnesium, we got the right trend, as we expected for single salt. Copper binds strongly, so it will not go through. But all the other ions, we got something that we could not explain. So again, we will see how we can explain it later. And again, these are a different concentration of the salts. So zinc, goes very fast, even though its binding energy is just intermediate. Now we can also here define a single salt selectivity, which again, doesn't make any sense from practical point of view, but you can define it just by the flux of copper in a single salt experiment divided by the flux of nickel in a single salt experiment. And we see some numbers here that do not make sense, but again, all these single salt selectivity, it's not as important. Now let's go to the mixture. And here we are starting to see something. So when you have a mixture of copper and nickel, copper always moves fast and nickel little. The copper and magnesium I already showed you earlier. Copper will move much faster than magnesium when both of them are in solution. And the same thing with copper and cobalt. But copper and zinc, we got things that we cannot explain. Copper binds stronger than zinc. So we can say that nickel, cobalt, and magnesium, nickel, cobalt, and magnesium behave as you expect. They will have lower flux from copper because copper binds strongly. But the zinc has higher flux than copper, and it's a big question mark. Now let's look at this data, and we can define selectivity. If you define this ratio of the fluxes, we can get selectivity, and we get very high selectivity. Again, these are a different set of experiments. Again, copper and magnesium, we got very high selectivity. Again, a lot of error bars because magnesium, it's hard to measure it. Almost nothing comes through. So we get very high selectivity for copper and nickel, copper and cobalt, copper and magnesium, although not in line with the binding energy, but we cannot explain the copper and zinc. And this is problematic. So, and this brings me sort of like to the last slide that I would like to explain what's happening there. And it's a very, very crowded slide. So we said, okay, each of these ions, as I showed you earlier, inherently, each of these ions inherently has different flux. And we cannot explain why, maybe because of the slight differences in size. So let's now divide the flux of this ion that you measure in a mixture to the flux of this ion just as a single. So for example, here for the copper with nickel, we can divide the flux that you get from the copper in a mixture, which is just the flux here, divided by the flux from a single salt experiment of the copper. And we see for the copper, it's not slowed down. Always you get high ratio of this flux in the mixture compared to the single flux of the copper in a single. But when we go to the lower binding, again, these have lower binding, the copper, nickel, zinc, cobalt, magnesium. If you go, let's go here. For the cobalt and zinc, we see that when they are in a mixture, the cobalt and the zinc will move slower than the copper. And the same thing with the magnesium, moves slower than the copper. And most importantly, we present this ratio that I explained here as a function of the binding energy difference. So we see that strong correlation to the binding energy difference of this. We want these other ions to move slower than the copper, and you can tune it by the binding energy difference when you do this normalization. And if you look at this data again, I can just present the selectivity of a mixture over the selectivity of the single salt, and we see that the selectivity of the mixture is correlated to the binding energy difference beautifully, and that we can even get selectivities based on this definition of close to 100. So again, binding energy difference is the key to tune the selectivity between ions that have the same size and the same charge. So to conclude the first part of my talk, transport of anions and cations is highly independent. They do not move as a pair, they move as individual. Intra-pore diffusion would be more important than partitioning. Selectivity between nearly identical cations is possible with membranes via host gas chemistry, the binding with the immunodiacetate, and this selectivity can be tuned by the binding energy difference. So to conclude, again, most of the work of the reverse osmosis was done by Chen, and the work of selectivity was done by Ryan, and I would like to thank the group and you for your attention. Thank you.
Thank you, Manny. It was really inspiring talk. Learn a lot. I have a lot of questions, but I will first let the audience ask. I see the message here. There is a question from Professor Huanting Wang. He says, in your ion transport measurement, how does the electric potential affect ion transport? This is the first question. Second one, if a hydraulic pressure or concentration gradient is applied instead, how does this affect ion transport behavior in your polymer membrane? Thanks. Actually,
So
I have the same question.
Yeah. I mean, we wanted to study fundamentally, so we use this experiment just by diffusion or by electrochemical migration. In a real operation that you want to have high throughput, you need to apply either pressure, so you'll have convection, or in electrodialysis, you apply electric field. And we do not know yet because we have not done these experiments. We expect that there will be the same trend, but quantitatively, we think there will be different value. And this is what we are studying now. So it's a good question.
Oh, that's very nice, yes. I think typing question that will take some time. We will wait for another questions. Actually, I have a question about the theory you just showed. That you mentioned that the binding energy of the ions to the separation layer polymer chemistry will have a real strong correlation with the selectivity. Is there something with pore size steric effects on the speed of your transport of ions? The steric effect.
Yeah, it's also a very good question. We have a layer by layer membrane, and you know that this layer by layer membrane also will have some rejection and some partitioning. So we think that also the selectivity may not be affected by it a lot, but the rate of transport probably will be affected. So it's not the most ideal system to study because you cannot control the pore size in layer by layer. And we are now starting by building a very well-defined channel to study it more, more carefully. But yes, like the potassium channel, the way it works, you also need to have small pore because the ions need to dehydrate first and enter. If it's very big, they will not dehydrate, and then you will have completely different behavior. So we still need to have small pore to induce dehydration.
Okay. There is coming another question. The size effect and charge exclusion, which one is dominant for membrane? Or if two factors were co-effect?
You're talking about the first part of my talk or second part of my talk?
I think
Oh,
they
the second.
basically want to know the mechanism, which one, the size and the charge effects. Which one
For
is
reverse
important?
osmosis membrane or the host gas chemistry, they are completely different. The host gas
Oh.
chemistry is all about chemistry and the interaction, and it's not only charge. You know, the immunodiacid are negatively charged and the cations are positively charged, but also the binding energy. For reverse osmosis, both of them are important. You know, the size, because you know you need to have a dehydration and steric effect, but also I showed you that the diffusion inside the membrane, the interaction with the functional group is also important. So
Yeah.
both of them, I think, are important.
I think his question is related to the first part. Then there is another question about the second part of the talk. He said that I'm confused for the second part. The separation of copper, the rate of magnesium is suppressed in the mix. Why?
It's all because of the principle that I showed earlier. Once you have, it's exactly like the potassium channel. The sodium is smaller than potassium, but it doesn't go through because it cannot interact appropriately with the functional groups inside the potassium channel. The same thing here. Copper interacts very effectively with the amino diacetate and not magnesium. And because of this, the hopping mechanism, sodium just cannot enter. Or if it enters, it will diffuse very, very slowly. So this is the same principle of the potassium channel in principle.
Yeah. Okay. There come another question. In the electrochemical system for individual ion transfer analysis in RO, will the proton and OH transfer, which is faster, interfere with the final ion transport? So
I think we did that. We analyzed and we are almost confident that the protons and hydroxyl will not impact the result. Of course, they will have some small effect, but they will not impact it. To be mostly by either the sodium or the chloride. And we work at a pH around 6. So we do not think that the proton and hydroxyl will have an important effect. And we prove it. If you take a look at the paper, it was published in Science Advances. I mean, we explain it there.
Okay. There is another question. In comparison with the first part, in the second part, what is the concept of interactive transport for cation selectivity?
Again, the first part and the second part really are quite different. The concept of the second part is just through the interaction with the, you need to have the right binding site and through interaction and hopping from site to site. And this is not the case in reverse osmosis membrane. This is just how to achieve highly selective membrane. And indeed, the principle is not much different than liquid membranes. In liquid membranes, we implement a sort of similar concept.
Yeah, I think the concept you introduce is quite clear. It's also very important for people to design their future membranes. Manny, I'm sorry, because the time limit. No, hold on. There is another question coming out. I think this is the last one. I will allow the last question to go on. Thanks, Professor Manny. Very nice presentation. For the second part, have you explored the selectivity between monovalent ions?
No, we took the easy part because we cannot be as good as the potassium channel. So we took immunodiacetate that we know binds very effectively to divalent. The next challenge is to find the right host gas chemistry for monovalent like lithium and sodium. So this is a challenge for you, the young people here.
No, just inspired by this question, can you put some crown ether to your layer valence system and to create
I think it's excellent. If you can put the crown ether, the right spacing and bind them, I think it's yes. And some people working on it. So crown ether can be, it's host gas chemistry, you're right. But again, you need to have them in the membranes and the right distance and bind them. And it's not easy to bind a crown ether because some people just put them physiosorption and they can leach out.
Yeah. Thank you, Manny. The time is up.
Very great question.
Very
Really,
interesting. I look forward to see you next time. Thank you.
Okay, great. Thank you so much, and I'll see you in a...
session.
So I can log off from this Zoom.
Yes, you can. Yeah. Thank you.
Okay,
We'll
great.
go to the next session.
Okay, thank you all.
Thank
Bye.
Have a nice evening. Bye.
Thank you, Manny.